Hello and welcome to this video. I am Karnesh Jory, and in this video I will be talking on POSIX semaphores. We have two terms here, semaphores and POSIX semaphores. What is a semaphore? Semaphore is a system of visual communication. Originally it was done using handheld flags, and the different position of the flags represented different characters, numbers, etc. Semaphores were used in railways. This is the upper quadrant semaphore, which means clear. Track is available and the train can go. If the lever was horizontal, it meant danger and the train must stop till the signal became clear. Then we have the traffic lights, where red light indicates danger, that is stop, and green light gives the clear signal to go. In all these cases, there is unambiguous communication happening, indicating either danger, that is stop, or clear, which means go. The use of semaphores in programming was invented by the great Dutch computer scientist E.W. Dijkstra in early 1960s. It was a seminal contribution in the field of concurrent programming. If you are developing a program which would always run as a single process, single thread of execution, and has dedicated database, well, you don't need semaphores. But if you have a program with multiple processes and or multiple threads and or shared database, semaphores can be a great help. Suppose there are two processes, P1 and P2, and there is a data segment which is shared memory, and this shared memory is mapped to the address space of both processes. So this data here is available to both processes P1 as well as P2, and there is a variable x in this data space. Now there is a program which says if x is equal to 7, increment x. Let's say this statement is in both processes, and suppose x is 7. So P1 process comes to this if statement, finds x is equal to 7, and then it is interrupted by the scheduler. So it goes out of execution and P2 starts executing. And P2 comes here, it also finds x equal to 7, goes ahead and increments it. Now x becomes 8. P1 comes back into execution and thinks that x was 7, and it also increments it, so x becomes 9, whereas the aim of both processes was to make x 8 if it was 7. So this kind of error has happened because there is no protection. Both processes can read and write at the same time. So it is here that we need semaphores to protect this kind of situation. Another example, suppose there is a system log process whose job is to log messages to a central log file. Any process that wants to log a message writes the message in a central buffer and signals the system log process, indicating that a new message to be logged. This signaling can be done by using semaphores. Remember, there may be a lot of processes wishing to write log messages around the same time. We have seen some examples where semaphores are useful. But what is a semaphore? A semaphore is an integer object. It behaves like an integer. It is non-negative. Its value is either 0 or positive. It is kernel managed. What I mean by kernel managed is that operations on semaphores need to be provided by the kernel, as one particular semaphore might get operated in multiple processes. There are two basic operations defined for semaphores. These are P and V. P and V are the first characters of Dutch words proberen, which means to try or attempt, and verhogen, which means to increase. For psem, If semaphore's value is 0, the call blocks till sem becomes positive, and then sem is decremented and call completes. If multiple processes are blocked in P operation, only one of them will succeed at a time. In V operation, semaphore is incremented. Both P and V are atomic operations, which means all or nothing. That is, either all processing for P or V is done or nothing is done. There are alternate names for P and V operations. These are wait and signal, down and up, acquire and release, pend and post, and procure and vacate. There are two kinds of semaphores: System 5 semaphores and POSIX semaphores. System 5 semaphores have been a part of Unix systems since the early 1980s, and these are also available in Linux. POSIX semaphores are as defined in POSIX 1993 standard for real-time extensions. System 5 semaphores are complicated and a little difficult to use. POSIX semaphores have been available since some time after the millennium and have a simpler interface and are easy to use. There are two types of POSIX semaphores. The first type is the named semaphores. These semaphores have a name. The name starts with a / and is followed by one or more characters, none of which can be a slash. The second type of POSIX semaphores are unnamed. These do not have a name, and a program using POSIX semaphores needs to be linked with the pthread library. Semopen is like open for files. It makes a POSIX semaphore available for operation. The first parameter is semaphore name, which starts with a / and has one or more succeeding characters, none of which is a slash. Next parameter is oflag. If oflag is ocreate, the semaphore is created if it does not exist. If you use ocreate as a flag, you need to use the second form of semopen, which has two additional parameters. The mode is the permissions for the semaphore, and the last parameter is the initial value of the semaphore. If you use ocreate as a flag and semaphore exists, mode and value are ignored. And if you use ocreate and oexcl as flag and semaphore already exists, semopen returns with an error. When semopen is successful, it returns a pointer to the semaphore, which can be used in subsequent calls. The semwait system call provides the P operation for the semaphore. If the semaphore value is greater than 0, semwait decrements the semaphore and returns. If semaphore value is 0, semwait waits for the semaphore to become greater than 0, decrements it and returns. Semwait is an atomic operation, which means if multiple processes do a semwait, only one will be able to complete it from start to finish at a time. The sempost system call provides the V operation for a semaphore. Sempost increments the semaphore. The semunlink system call removes the semaphore associated with the parameter name. On Linux, POSIX semaphores are created in a temp file system mounted at /dev/shm. We can see the directory of /dev/shm. The semaphore names are prefixed with sem dot, the dot replacing the / in the name. Semaphores are persistent, and if not removed by semunlink, it will exist till the system shutdown. You can use the rm command to remove semaphores in the /dev/shm directory. As an example, consider a process having producer and consumer threads and an array of buffers for passing data between producers and consumer. A producer produces a character string and writes it in a buffer. The consumer, which is the spooler thread, reads it from the buffer and prints it on the terminal. The key problems are: 1. Two producers must not write on the same buffer. 2. If there are no buffers available, that is, all buffers have data which has not been read by the spooler thread, a producer wishing to write data in a buffer must block, and such a producer should get unblocked as soon as a buffer becomes available. 3. After putting data in a buffer, a producer should be able to signal the spooler that there is data in a buffer. This is the example program. We have got 10 buffers. Each buffer can keep 100 characters. Then there are two indexes, buffer index. Buffer index points to the next empty buffer, and buffer print index points to the next buffer to be printed by the spooler. And then we have got 3 semaphores. First is the mutex sem. This is for the mutual exclusion of the buffers, so that no two threads should access the buffers at a time. There is a buffer count semaphore which keeps the number of buffers available for writing. Then there is a spool signal sem which is used by the producers to signal the spooler that there is data available in the buffers for it to print. So first we create the spooler and then we create the 10 producer threads, and let's look at producer. A producer gets a buffer by doing a P operation on buffer count semaphore. Then it does a P operation on mutex sem. We have to make sure that the buffer index is not manipulated by more than one producer at a time. So this producer gets the buffer index, that is the index at which it can write in the buffers, and then it releases the mutex sem and it writes a string in that buffer, and then it signals the spooler. It does a V operation on spool signal sem and tells the spooler, look, there is data in the buffers, you go ahead and print it. Next we have the spooler. The spooler waits for this spool signal sem. It does a P operation, it blocks here. Suppose there were no producers, then it would just be blocking on spool signal sem. Once spool signal sem is signaled, that is a producer does a V operation on spool signal sem, this P operation passes, and then it writes a data pointed by buffer print index. It increments the buffer print index and then it releases a buffer. It does a V operation on buffer count sem. We can compile this program, gcc POSIX Semaphore example.c -o POSIX -lp thread, and we can run this. In the previous example, the semaphores have a name. We have sem mutex, sem buffer count, and sem spool signal semaphores. That's not really necessary. After all these semaphores are being used in a single program, and we can instead use unnamed semaphores. Unnamed semaphores do not have an external name. So semopen and semunlink system calls are not relevant for unnamed semaphores. Instead, we have a seminit system call. With seminit, we get an unnamed semaphore. In case of named semaphores, semopen allocates space for semaphore objects and returns a pointer to it. In case of seminit, we define a semaphore object, that is, we allocate space and pass a pointer to it in the system call. The second argument indicates whether the semaphore is shared between threads of a process or multiple processes running on the system. If P shared is 0, it is shared between threads of a process. So an unnamed semaphore should be defined high enough in the program so that it is visible to threads using it. If P shared is non-zero, it means that the semaphore is shared between processes. So in that case, semaphore should be defined in a shared memory segment which is attached to the process using it. When an unnamed semaphore is no more required, it can be destroyed by using the semDestroy system call. The semDestroy system call destroys the unnamed semaphore pointed by sem. And this is the same example program as before, except that we are using unnamed semaphores in place of named semaphores. Here we are defining the semaphores, semT, mutex sem, buffer count sem, spool signal sem. Earlier we had defined pointers, now we are defining the semaphores, allocating memory for them. and we do a sem init for these 3 semaphores. Then we create the spooler, we create the 10 producer threads, and everything happens as before. This is the producer, the code is as same as before, and here again the spooler, the consumer, the code is same as before. You can find all the information given in this video and program source code at http://bit.ly/POSIX-Semaphores. With this, we have come to the end of this video. Thanks very much for watching. Have a good day.